Hello and welcome to the session number 5 of the Theory and Application of Network Coding course. So in this session we will talk about multicast connections, and I also will talk about how to model a communication network through a graph. So in multicast connections the goal is to send data from a single source S to a set of terminal nodes, set of, for example, K terminal nodes from T1 to Tk. Each terminal needs to be able to decode all of the packets sent by source nodes. So the unique property of a multicast connection is that all packets needs to be decoded by all terminals. The rate of the multicast connection will be the number of packets that can be decoded at each terminal. So suppose by simplicity that we model our network by a graph. So a graph can be both directed and undirected graphs, and we will mainly focus here on directed graphs, but however we will also consider undirected graphs. So in undirected graphs, and example of this graph depicted here, we don't show any direction on any link, and this basically means that we can send data in any direction we like. For example, in this graph, if we want to send data from S to all terminals, we can send it along a tree. So for example, we can send some set of packets from S to T1, another is from S to T3, and another by S to T2 using in the directions that I am showing right now. And this will be one more traditional way of doing this by forwarding packets over a link of a tree that connects source to the set of terminals. So what we will assume, just for the purpose of our discussion, that each link has the same capacity, and each link can send exactly one packet per time unit. So for example, it can be a second or some other unit. And this will simplify our discussion, but also we'll be able to model links of higher capacity by just splitting them into multiple parallel links in this network. So the main theorem of the multicast, or network coding for multicast, is very, very powerful. So it's basically said that suppose we can transmit data at rate r to each of the terminals separately, then we can transmit at rate r to all terminals. So this is basically saying that to analyze the rate that we can transmit in a multicast connection, we just need to find out what is the rate, what's the maximum achievable rate to each terminal, and take the minimum. So it turns out that analyze each terminal separately can be done very efficiently using traditional tools such as Menger's theorems or min cut max low theorems that we'll discuss shortly. So in general, as I said, the network can be modeled as a graph. So in this particular case, and this example on this slide, the graph is directed. In directed graph, each link has a direction, and we can only send data according to this direction. So we cannot send data in the opposite direction on this link. Again, in most general case, we have a set of source nodes. For example, here nodes are depicted by green vertices, so we have 4 source nodes. And we have a set of terminal nodes. So here we have 4 terminal nodes depicted by red vertices. And again, we make an assumption that each link can transmit 1 packet per time unit. So this is just important for uniformity, but in general, we can also model links of higher capacity by just splitting them over parallel links. And the goal is transmit as much information as possible between sources to set of terminals. So in general, this problem is complicated, as we'll see. For example, if you have multiple Unicasts, then we have pairs of nodes. And sometimes we can define the rate as a minimum rate among those multicast pairs. So in the beginning of this course, we'll restrict ourselves to multicast connections. So in multicast connections with a single source S, we want to transmit information between the sources to each of the terminal nodes here. And again, we want to maximize the number of packets that can be decoded at each terminal node, subject to this limitation that each link can only send 1 packet per time unit. Again, if you say that rate of the multicast connection is 4, it means that at each time unit, each of the terminal nodes can decode 4 packets. and the same set of 4 packets. So the source nodes will receive 4 packets per time unit, forward them over the network, and each of the terminal nodes will be able to decode each of those 4 packets. So let's us first to define the fundamental notion of a cut in the network, and of course some of you might be already familiar with graph theory, so this is just a reminder. So why we need it? Because the cut will determine the number of packets that we can send to each node separately, and of course it also will determine the rate of multipass connection if we consider all cuts that separates a source or a terminal. So in general, a cut is a partition of the nodes into two subsets. For example, here we have one subset V1 and another subset V2. So this partition defines a cut from V1 to V2, and the size of the cut is equal to the total capacity of the links between nodes in V1 and nodes in V2. So for example, in this case, all blue links, V1 is actually includes those links, and V2 those nodes, and V2 includes the rest of the nodes in this graph. So all blue links here, the links that connect nodes in V1 to nodes in V2, and the size of this cut C will be equal to total capacity of links in this cut. Since we consider that capacity of each link is equal to 1, then the size of the cut will be just a sum of the will be equal just to the total number of links in this cut. So in directed graphs, the ordering of sets V1 and V2 is important. So for example, if we have a directed graph and we have cut between V1 and V2, we only count links that connect nodes in V1 to nodes in V2. We don't count links in opposite directions. So for example, if there exists a link in opposite direction, we will not count this link, and this link actually will contribute to the cut from V2 to V1. So why cuts are important? Because of the following Menger's theorem. And Menger's theorem characterizes the total number of edge-disjoint paths between S and T, and claims that the total number of such paths is equal to minimum capacity of a cut that separates source node S and destination T. For example, consider the case that we have one source and one terminal. So this is basically refers to the case of Unicast. And what Menger's theorem says that the minimum number of edge-disjoint paths, so suppose we want to find the maximum number of paths that connect S and T. So each of the paths will connect source node S with destination node T, but we don't want those paths to share edges, right? So those paths will be edge disjoint. And of course, if we found edge disjoint paths, that basically means that we can send edge packets per time unit. And as we'll see, it's easy to show that this will characterize the total amount of information that can be sent from S to T in the case of Unicast network. But first, what Menger's theorem says that the maximum number of such cuts is equal to the minimum capacity of a cut that separates S and T. And in one direction, to prove this theorem, it's pretty simple. So if you can find edge-disjoint paths, then any cut that we consider in the network that separates S and T, so separates S and T, it means that S will be in V1 and T will be in V2. So any such cut must have at least H edges. Why it must have at least H edges? Because those disjoint paths, they will cross this cut, right? So each of those paths will cross this cut at least once. It can actually cross even multiple times. But at least one time this cut will be crossed. So again, going in one direction is pretty obvious. So if we have a network, and suppose we have S belongs to V1 and T belongs to V2. So any cut that separates So the proof of this theorem in one direction is pretty obvious, right? So it's easy to show is if we have H disjoint path that connects S and T, then minimum capacity of any cut that separates S and T is at least H. So to show this, to see this, consider any cut. So suppose we have cut V1, V2 such that V1 includes source node S and V2 includes destination node T. By the way, this is what we mean by saying that a cut that separates S and T is that S will belong to V1 and T will belong to V2. So if you consider such cut, we see that each of the disjoint paths that connects S and T will cross this cut at least once. For example, P1 will cross this cut here, P2 will cross it on this edge, and P3 will cross on this edge. So then the capacity of this cut has to be at least H. It actually can be, in some cases, can be more than H, because a path can cross this cut multiple times, more than one time. So what Menger's theorem says that is also true in the other direction. So if we have certain graph, so we have source S and source T, and then if any cut that separates S and T has at least H edges, so it doesn't matter how we partition this network into two sets, and again S must belong to V1 and T must belong to V2, but if any such cut has at least H edges, then it's possible to find H disjoint paths between S and T. So the proof of Menger's theorem is beyond the scope of this course, but if you're interested, you can look at any book on graph theory. And this is related to duality theorem and linear programming. So it's very, very fundamental theorem. So how it's helpful to us? So first of all, we can see that because we are interested in maximum amount of information that we can send from S to T. So then the minimum capacity, if you want to suppose it's possible to send information at rate H, then it's pretty easy to see that this requires a cut condition. Again, this is a very simple information theoretic argument which says that suppose we have source S and destination T, and suppose we possible, so there is a way to transmit H packets. So then any cut that separates S and T, so suppose we have cut V1, V2, again V1 contains S and V2 contains T, so then the fact that we can transmit H packets from S to T per time unit implies that the capacity of this cut is at least H. So there is at least H links that cross this cut. And the reason for that is that if we had less than H links, so it's no way the information can be transferred from nodes from V1 to nodes in V2, even if we had infinite connectivity. So suppose we have infinite capacity edges between S and the nodes that are connected to nodes in V1 that connected to nodes with V2, and we have infinite capacity edges that connect nodes in V2 to T, right? Still, if you have less than H edges, it would not be possible to transmit H packets, right? So this is pretty simple argument that you can think about of how to do it. So then from this argument it follows that first the claim number 1 implies claim number 3. So then from Menger's theorem we know that claim number 3 implies claim number 2. So if its min cut is at least H for any cut, then we can find H disjoint paths, and claim number 2 implies, or condition number 2 implies condition number 1. Of course, if we have H disjoint paths, we can communicate at rate H, so we can just send packets along each of those paths, and we will be able to reach the destination nodes. So one of the main implications of this theorem is that we can fully characterize the capacity of the network in the case of one terminal. And the capacity or rate of maximum rate of information that we can transmit between S and T will be equal to the minimum cut that separates S and T, right? So then it's fully characterized, and and also what we can see from here that if just our purpose to maximize the rate of connection between S and T, we don't really need to use or any of the network coding techniques. We can just send packets uncoded over those disjoint paths, and we can achieve the required rate. So in this case, the network coding doesn't give any advantage. So we can transmit information using network coding at the same rate that we can transmit it using traditional routing. However, as we see, the coding advantage is much higher in case of multicast connections. Also, the relation between min cut and max relation between minimum cut of the network and maximum number of disjoint paths in this network is related to flow interpretation. So in the theory of network flows, each link has a certain capacity. Again, here we have each link can have capacity 1, and flow over this link is some value that satisfies flow conservation constraints. So for example, if you have a flow, so suppose this is link E1 and FE is a flow of link E1, so of course flow of any links should be less or equal than capacity of this link. So suppose C of E1 is the capacity of this link. We assume for simplicity the capacity of all links is equal to 1. So then we assigned values of flow. So flow needs to satisfy flow conservation constraint that in each intermediate node in the network, the total amount of flow that enters this network is equal to total amount of, so for each network node, the total amount of flow that enters this node is equal to the total amount of flow that leaves this node. So this is true for each intermediate node on the network, which is not including source and terminal nodes. So in this case, what we will see is that, for example, if you want to find out what is the maximum amount of information we can send from S to T1, we can use it using this red flow, in which in each red link we send flow of value 1. So we also see that in case of unit capacities, and if this flow is integer, that means that FE can belong only to 0 and 1, there is a strong connection between the flow and the number of disjoint paths. So for example, here we can look on those red links as a red flow, but also we can think about 3 disjoint paths that connect S to T1. So now what, and in general, for unicast connection, if we can find in the capacity of each link is uniform, so the size of maximum flow is equal to the maximum number of disjoint paths, because optimal solution to this minimum max flow problem, so max flow problem is maximize the total amount of flow that exits the source node, or the same amount of flow that enters the terminal node. So maximum solution to the maximum flow problem, at least one of those solutions is always integer. So this basically means that amount of maximum flow that we can send from source to each terminal is equal to the number of disjoint paths from the source to this terminal. So in this network, we will see that we can obtain maximum flow or find maximum number of disjoint paths between source and each terminal. So here we have red paths. So if you look on terminal T5, we can use 3 edge disjoint paths like here. Okay, and those paths don't share any edges. So then what our main theorem of network flow says, that if we can communicate with rate R to each terminal separately, then we can establish multicast communication of rate R. And this basically means in cut conditions that if capacity of any cut that separates source and at least one of the terminal is at least R, then we can establish communication of rate R. So this is basically connection between cut conditions. So basically capacity of certain cuts. So those set of cuts will be set that separate source and at least one of the terminals. So if you check this cut, cut needs to be larger. So total number of links in this cut needs to be larger than the rate of the multicast connections. So this, therefore, what we can do, we can characterize the maximum rate achievable multicast connection and capacity for certain cuts in this network. So let us consider this simple butterfly network, and let us demonstrate this min condition on this network. So the main theorem of multicast said that if I can communicate with each terminal at rate r, then I can communicate with all terminals at rate r. So in this case, I can communicate at rate 2 between source S and terminal T1. Certainly, I have two disjoint paths shown here by green. And equivalently, I can show that any cut that separates S and T1 has a capacity at least 2. The same I have to terminal T2 because it's completely symmetric. So we have those two red paths that connect S and T2. Equivalently, any cut that separates S and T2 has capacity 2. So this cut condition that says that we can communicate to T1 at a rate R if any cut that separates S and T1 has rate R, and S and T2 has rate R as well. So this condition is equivalent to saying that any cut that separates S and at least one of the terminal must have rate R. So this is the condition for multicast connection. So again, let me repeat it, right? So if we consider any partition such that this partition in set V1 must include S and possibly include some of the terminals, and set V2 must include at least one of the terminal. It doesn't matter how many. So for example, it can include T1, T2. So any of cuts that satisfies this condition, if I consider all cuts such that V1 includes S and V2 includes one of the terminal, doesn't matter which, if I'm taking minimum capacity among all those cuts, this will be the maximum rate achievable by multicast connection. So for example, in this butterfly network, I can take any cut. For example, one of the cuts can be like this, right? So this cut separates S and T2, or this cut which separates S and T1, or I can take a cut that separates both, separates S and both T1 and T2. If I'm taking the minimum among all of those cuts, this will determine the maximum rate I can achieve on this multicast connection. Also, another flow interpretation is very nice, right? So we can see, for example, why we cannot use routing in this network, why we really need to use coding. Because if we want to use routing, we need to send data. For example, if we decide on sending A here and B here, then the data to T1 with routing must follow those disjoint paths. If we send data without coding, so it's not just forwards, there must be two disjoint paths. So the data needs to be sent, because you can trace how the data is sent. It's always will send over a link disjoint or edge disjoint path. But then we see that those paths, disjoint paths between T1 and T2, that those two sets, they actually clash, right? Because if we're sending A over this link and B over this link, then we need to do the same here, right? Because it's the same network. And then what we see that for terminal T1, we need to send B, right, according to those green paths, and to terminal A, we need to use this bottleneck link in the middle to send A. So then we see that routing solution is not possible, because those two sets of paths, they want to send different data over the same link. And this can be actually resolved by using network coding, and eventually we can achieve capacity by using this technique. So this concludes lecture number 5. Thank you.